In this video, I'm going to discuss about the sampling distribution of sample mean. If x is a random variable and this is the distribution of x with mean is equal to mu and variance is equal to sigma square. The mean of the random variable is denoted by Ex with the value is equal to mu. The variance of the random variable x is denoted by Varx with the value is equal to sigma square. Now I'm going to do sampling to select a sample with the sample size 4, which means I will have 4 observations in this sample. Let's say x1, x2, x3, and x4. Now I have already chosen one sample with sample size 4 and I name it as sample 1. For this sample, I'm going to calculate the mean where I sum up all the 4 observations and divided by 4 because the sample size is 4. Since this is the mean of the sample 1, so I name it as sample mean 1, which is denoted as bar x1. Next, I'm going to select another sample with the same sample size. Let's say x1, x2, x3, and x4. These 4 observations now form another sample called sample 2. When I calculate the mean of this sample, so I name it as sample mean 2 and denoted as bar x2. Again, I am going to repeat the same step for sample 3 with the same sample size. I start from x1, x2, x3, and x4. These 4 observations form the sample 3. The mean of this sample 3 is sample mean 3, which is bar x3. After the sample 3, I continue to do the sampling to get as many samples as possible, and now I have many sample mean as well. Now when all these sample means are put together, then these sample means will form another distribution, that is the distribution for the sample mean. This distribution of sample mean is called sampling distribution of the sample mean. But now we do not know what is the mean and variance of this distribution. Will it be the same as the population distribution X? Now I'm going to find it out. First, I'm going to find the mean of this distribution, which is the mean of the sample mean. The mean of the sample mean is denoted as E bar x. Since bar x is the sample mean, which is the sum of the observation divided by the size of the sample size. Now I'm going to take out the constant n. N is the sample size. Now for each of the observation, I separate this one becomes ex1, ex2, and so on. So since x1, x2, and x3 are taken from the same distribution, So means the value of mean must be the same, that is mu. So when I sum all together, the sample size is n, so altogether I have n mu. So when I simplify, it is equal to mu. So here we find that the mean of the sample mean is actually same as the mean of the population distribution. Next, I'm going to find the variance of this distribution, which is the variance of the sample mean. The variance of the sample mean is denoted as VAR bar x. So now I substitute the bar x, that is the sample mean, where the sample mean is sum of the observation divided by the sample size. So next I'm going to take out this constant. But when we try to take out this constant, from what we have learned before, when taking out any constants from the random variable, this constant becomes square. So therefore, when I take out 1 over n, it becomes 1 over n squared. Then I separate the variance for each of the x, and since all these x1, x2 and x3 are taken from the same distribution, so the values of the variance is the same. Now I sum up all the variance and it is equal to n sigma squared. So when I cancel off one of the n, it is equal to sigma squared divided by n. That is, the variance of the sample means is equal to the variance of the population x divided by the sample size. So as a conclusion, when a sample with size n taken from a distribution x, the mean of the sample mean is same as the mean of the population distribution, but the variance of the sample mean is equal to the variance of the population divided by the sample size. Now we are going to discuss about the distribution of the sample mean. When a sample of size n is taken from a population x, if x follows a normal distribution with mean of the distribution is mu and variance is sigma squared, then the sample mean also follows the normal distribution with the mean is same as the population, but the variance is equal to the variance of the population divided by the sample size. If x follows binomial distribution or Poisson distribution or other distribution, then the distribution of the sample mean is unknown. However, based on central limit theorem, if the sample size is sufficiently large, which is sample size is greater than or equal to 30, then the distribution of the sample mean is approximate to normal distribution. Now we are going to discuss the distribution of the sample mean based on the different types of distribution of the random variable x. Now first, when the x is a normal distribution with mean is equal to mu and variance is sigma squared, then the distribution for the sample mean is also normal distribution with mean is mu and variance is sigma squared divided by the sample size without using central limit theorem, and it is valid for any sample size. And if x is a binomial distribution with mean is np and variance is npq, then the distribution of the sample mean is approximate to the normal distribution provided that the sample size is greater than or equal to 30 based on central limit theorem. So in this distribution, the mean of the sample distribution is equal to NP, and the variance of this distribution is NPQ divided by the sample size. So in this case, this N is the parameter of the binomial distribution, but the sample size is M. And if X is a Poisson distribution where the mean is mu and the variance is also mu, then the distribution of the sample mean is approximate to the normal distribution, provided that the sample size is greater than or equal to 30 under central limit theorem. So in this distribution of sample mean, the mean is mu and the variance is mu divided by the sample size. And if X is an unknown distribution with mean is equal to mu and variance is equal to sigma square, then the distribution of the sample mean is approximate to normal distribution under central limit theorem, provided that the sample size is greater than or equal to 30, where the mean of the distribution of the sample mean is same as the distribution of the population, but the variance is the variance of the population divided by the sample size. Now after the theory, let's try some example, and I'm going to show you how to use the distribution of the sample mean in answering question. For this question, the masses of bags of sugar produced in a factory are normally distributed with mean 1.5 kg and standard deviation 0.5 kg. Question A. Find the probability that a randomly selected bag has a mass of at least 1.3 kg. First, we are going to define the random variable. For this question, the random variable is X, that is the mass of the bag of the sugar. So since this question is finding the probability about the mass, so in this question we are not going to use the sampling distribution of the sample mean, but we use the probability distribution of the X. So the distribution of this variable X is normal with mean 1.5 with variance is 0.5 squared. So now we are going to find the probability of mass at least 1.3 kg. That is probability of X greater than or equal to 1.3. And then we are going to change the X into Z score, and 1.3 minus the mean and divided by the standard deviation. So after simplifying, we find that Z is greater than negative 0.4. Since negative 0.4, it is not in the standard normal table, so we are going to change to Z less than 0.4. Then from the table, we find that the probability is 0.6554. Now question B. Find the probability that the mean mass of 50 randomly selected bags is at least 1.3 kg. In this question, we are going to use the distribution of the sample mean, because this question is finding the probability of the mean mass. Mass is the random variable X. Mean mass means bar X. So in order to answer this question, we need to know the distribution of bar X. Since the random variable X is normally distributed, so the sample mean bar X also normally distributed. And the mean of this distribution is 1.5, but the variance of this distribution of the sample mean is the variance of the population divided by the sample size, that is 50. So now we are going to find the probability the sample mass at least 1.3 kg. So by using this distribution, I change the bar x to z, and 1.3 minus the mean 1.5 divided by the standard deviation 0.5 over square root of 50. So after calculate, z is greater than negative 2.828, and since this is a negative, so I change to z less than 2.828, and from the table I find that the answer is 0.9977. Second example. The number of misprinting in a page has a Poisson distribution with parameter 0.36. A random sample of 81 pages is taken. Find the probability that the mean number of misprinting of the sample is between 0.3 and 0.45. For this question, the random variable x is the number of misprinting in a page. And in the question, it is given that this random variable follows a Poisson distribution with parameter 0.36. So in this question, we are asked to find the probability of the mean number of misprinting. So number of misprinting is x. Then mean number of misprinting is bar x. So therefore in this question we are going to use the distribution of sample mean. Since the distribution of the random variable is Poisson, then the distribution of the sample mean is unknown. But because of the sample size is sufficiently large, which is 81, so according to the central limit theorem, the sampling distribution of the sample mean is approximate to the normal distribution, where the mean of the distribution is 0.36 and the variance of the distribution is 0.36 divided by the sample size, that is 81. And in this question, we are going to find the mean number in between 0.3 to 0.45. Now I'm going to convert the bar x into the z score. After simplify, z is greater than negative 0.90 and less than 1.35. So this one is equal to z less than 1.35 minus z less than negative 0.9. And z less than negative 0.9 is 1 minus z less than 0.9. Then from the table, so we find that the probability is 0.7274. Next example. The mass of a randomly chosen packet of a certain brand of sweets is normally distributed with mean 625 gram and standard deviation 8.5 gram. Find the least value of n such that there is at least 95% of the average mass of a random sample of n packets of sweets, which is at least 625.8 gram. In this question, the random variable is the mass, and this random variable is normally distributed with mean 625 and variance 8.5 squared. And in this question, how do we know that this question involves bar x? This is because this question involves average of mass. Mass is the random variable x, average is mean, so means this is mean of x, that is bar x. So before we proceed, we need to find out the distribution of the bar x. Since x is in normal distribution, so the distribution for bar x is also a normal distribution. and the mean is same as x, that is 625, but the variance is variance of the x 8.5 squared divided by the sample size. But now we do not know the sample size, so we leave it in terms of n. And this question given that the average mass is at least 624.8. So means the question average mass is bar x at least is greater than or equal to 624.8, and it is given also it is at least 95%. And we know that 95% is equivalent to the probability of 0.95. So at least 95% means the probability is greater than or equal to 0.95. So now when I continue, I'm going to convert the bar x into z-score. So when I simplify, and I find that this one is a negative value, so I change it to the positive value. Now from the normal table, I find that under 0.95, the value is 1.645. So means this value is greater than or equal to 1.645. So when I simplify this part, then I get this. And when I further simplify, I find that n is greater than or equal to 4887.76. And n should be an integer which is greater than 4887.76. Therefore, n is equal to 4888.